Hey everyone, thank you guys for coming out to another Tech Bytes event. For those of you who don't know, or this is your first time here, Spotify Tech Bytes is our tech speaker series where we have both internal and external speakers come join us on stage for a deep dive into a range of tech-related topics. Our goal is to increase knowledge sharing both inside and outside of Spotify. And today we have Neville Li with us, who's going to be talking about data processing with Scio.
Thanks. Well, thanks for coming. Today I will be talking about data processing with Scio. And Scio is an open source project that we built for data processing on Google Cloud. So let's get started. A little bit of an introduction. So my name is Neville. I've been here at Spotify for a little bit more than 8 years. Around the time we launched in the US. And the last couple of years, I worked a little bit on music recommendation. I was in the team that built Discover Weekly, Release Radar, and a few other features. And the last few years, I've been mainly working on data infrastructure. So I built libraries and tools for data processing, mostly batch and also streaming as well. So a little bit about Spotify. Hopefully you guys use Spotify. It is an audio streaming platform. So we have music, podcasts, and we have a lot of users from all these different markets. We collect data from user activity and also from labels like catalog, metadata. So we actually have a lot of data, and we build interesting features like music recommendation, ads targeting, and all sorts of other use cases with the data that we have. So the main topic of this talk, obviously, is data. So we're talking about the evolution of data processing at Spotify. And this is a fun image from about 10 years ago. This is one of the first Hadoop cluster at Spotify. And it was around the time when Hadoop was a brand new thing, and then some engineers decided to try it out and just build some servers in the football room. And this is actually one of the problem that they solved. The cluster was overheating a lot during the summer, and the engineer came up with this brilliant idea, like just install a curtain on the window, and then they solved the problem. So one of the first one, and it's been long gone since then. And we actually went through a couple of different iterations of Hadoop. So as I said, we first had an on-premise in the closet kind of Hadoop cluster. We went to Amazon Elastic MapReduce in the cloud, and because of the cost effectiveness and also the performance reasons, we moved back to on-premise. So at the time, maybe 2-3 years ago, when our on-premise Hadoop cluster was shut down, it was actually one of the larger clusters out there, 2,500 nodes. It was based in a data center in London, and it's storing a lot of data and also running a lot of jobs every day. So the stack we were running at the time, here's a little bit overview. Spotify started as a Python shop, so we used to write everything, backend services, data pipelines, everything in Python. We created Luigi specifically for building complex data workflows in Python on MapReduce. That was 8 years ago. And Python had a lot of problems, specifically like the performance problem, and also it wasn't working so well with the Hadoop ecosystem, which is mainly in Java. And also the lack of type makes it easy to write code, I would argue, but sometimes harder to reason about code, and also the correctness, and then hard to test. So around 2013, we started using Scouting, which is the Twitter library, built using Scala, a programming language, and then runs on Hadoop. And Spark was also brand new at the time, and we evaluated a little bit. We used it for some machine learning use cases. And at the time, streaming was also like a new cool thing that everybody's doing. And Storm was the tool of choice at the time. We used Storm for a bit for streaming, like real-time ads targeting and recommendation purposes. Storm has its own API. It's either Java or Clojure. And we also have a lot of like data analysts who mainly write SQL queries. And at the time, the SQL analytic tools on Hadoop of choice was Hive. So you write SQL query, which translates to MapReduce jobs. Moving on, maybe 4 years ago, we started evaluating Google Cloud because we decided that at a point, Spotify is grown to a size where it doesn't make sense to maintain our own data centers. It's hard to manage thousands of servers and like software that runs on them like reliably. And Google had a lot of experience, and particularly in the domain of data processing, Google was the pioneer. So we decided to like evaluate some of the Google tools. So and one of the first things that we evaluated was BigQuery. So the Hive that we were running at the time had a lot of problem. We were using Avro or text files, which is a row-oriented file. So to do any type of SQL query, even if you're just selecting a subset of the columns or rows, it has to do a full table scan, which is super inefficient. Google's BigQuery actually originated from their internal system and a paper that describes this columnar storage format. And the idea was originally from the relational database world, and it's a much more efficient way of storing and querying ad hoc data. Hive, on the other hand, also translates your job into individual MapReduce jobs. And in between each MapReduce job, there's a lot of shuffle going on and a lot of like the disk I/O, like writing temporary data to disk and read it back. And these are inefficient, and BigQuery has its own execution engine, which makes it much more interactive. So compared to, say, sometimes tens of minutes or hours of wait for a query to execute, sometimes the equivalent in BigQuery can take in a matter of seconds. And BigQuery has a pretty good integration with the other Google products, particularly Apache Beam, which I will get to in a bit. So a typical example querying the top tracks per month over Spotify, and we have daily partition of listening history, and it's usually 70, in this case, 70 terabytes of data, and we join that with a metadata table which maps track ID into, like, say, artist name or album name, and that's another 500 gigs. So this query runs on BigQuery that takes roughly 3 minutes, and then you only pay for the 5 terabytes that's actually processed instead of the full table scan, which is actually pretty great. So the adoption of BigQuery took off really quickly. A lot of users, even like product managers and like engineers, start using BigQuery to analyze their data. So it was the first product that we adopted on Google Cloud. So looking back some of the other products we have. So as I mentioned, we had Scouting mainly for batch processing, Spark for some machine learning purposes, and Storm for some real-time streaming use cases. The problem with that is we run all of these on a shared Hadoop cluster. So resource management and utilization has been a problem. So someone could run a big job and then blocks the execution for everybody else. And managing a cluster with many thousands of nodes is actually very challenging. Also, some of the frameworks that we use has a lot of tuning knobs, so you need to understand the internals like caching, the shuffling settings, and all these things. So it's not easy to write good pipelines on separate so many different platforms. And again, since we're moving to Google Cloud, these products don't work that they are not cloud native, which means we have to actually spin up Hadoop clusters on Google Cloud to actually run these jobs. So the next thing that we evaluate in evolution was Apache Beam. So what is Apache Beam? So there's a little bit of history. Google was the pioneer of data processing, and they introduced MapReduce paper about 10 years ago. Fun fact, a few days ago, I think a few days or weeks ago, Google announced that they finally killed off their internal MapReduce cluster. It's moving on to the latest thing I'm going to talk about. So Google introduced MapReduce, and then they introduced a lot of other papers that inspired many open source projects. So like the storage products, BigQuery, and columnar format, and both batch and streaming processing platforms. So about 4 years ago, they published another paper, Dataflow, which describes a new unified programming model for both batch and streaming processing. So before that, you have either batch or streaming, but never both. In this new model, you can write a pipeline once and argues that batch is actually just a special case of streaming. And they open sourced it, which became Apache Beam, and which became the tool that we built Scio on top of. So Scio, it's a library that we built and open source the name is actually Latin and means I know I can. And a lot of Scala libraries have names start with SC, and it's a data processing library, so and it's with IO, it makes sense. We just picked the name and it's stuck. And it runs on Apache Beam, as I said, which does unified batch and streaming processing, and actually has a decoupled programming interface and execution engine. So the programming interface called SDKs is where in our case, end users, developers write pipelines in and offers Java, Python, and Go SDK. We built Scio on Java. We actually have a couple of folks using the Python SDK for audio processing because Python is still like the most popular tool for a lot of the data science audio analysis use cases. And then the execution layer, which is decoupled from the SDK, can run on one of these many runners, like the Google Cloud Dataflow, which runs natively on Google Cloud, obviously. A few Apache open source projects like Flink, Spark, some of the more popular data processing tools out there. So what does the Beam model describe exactly? It tries to answer the 4 important questions about data batch and streaming processing. So what results are we calculating? Like, are we summing things up? Are we concatenating strings? Are we building sets of IDs? So that's the operation. And where in event time are results calculated? The event time is when the event happens, like when a user clicks a button and then gets logged on a server. And when in processing time, results materialize, because there's always a network latency. The log needs to be delivered from the backend service to the data processing engine. So there's some latency there. And because of the latency, we need to answer the last question: how do refinements happen? Like, what do I do when data is late? What's the definition of something, some time window is complete and I can start processing that? So again, the 4 questions and then how that relates to the different models of data processing. Classic batch treats everything as if they're in the same window and then it waits until everything is ready and then kick off the job. And then you can do windowed batch. You can have granular, smaller batch jobs processing a subset of the data. And streaming is more complex because your data can be late, like in this diagram, one of the red dots can be late data. So you need to decide whether I drop it or wait till it's available. And the last one is, what if I want to the accumulation part? What if I want to process my streaming pipeline as soon as possible, but also be able to handle such late data? So why did we pick Dataflow and Beam? And there are a couple of considerations. Well, obviously, one of the first, the most attractive thing is that now we have a unified batch and streaming model. We no longer have to maintain several different APIs and frameworks. And particularly in the case of Cloud Dataflow, it runs on Google Cloud, and it's fully hosted and managed, which means there's no need for us to maintain a Hadoop cluster or any type of operational cost. And Google has built a lot of their experience in big data into the product, like auto-scaling, workload rebalancing, all these nice features. And the last point, it integrates really well with the Google Cloud ecosystem. It comes with connectors to a lot of the Google storage products, like Bigtable, Data Store, PubSub, and Spanner. And the next question is, why did we choose to build a Scala API on top of Beam? Scala is actually pretty popular in the data processing world. I think Twitter was the pioneer of this idea and then took off with Scouting, Spark, and Flink. So there are a lot of data engineers already familiar with these APIs, and it's very easy to onboard them. And it's type safe and it's a functional programming language. So a lot of the concepts match really well to data processing, because after all, data processing is mostly taking an immutable data set from a data source, applying pure function transformations, and produce new immutable data sets. And a lot of these functions can be composable, so you can write complex pipelines relatively easily. And Scala also comes with a couple of popular libraries for data for numerical computation, like Breeze, which is a library for linear algebra similar to NumPy in the Python world. Algebra is a Twitter library for doing parallel approximation computation. And the the last point, which makes Scala very interesting, is that it's a great language for building advanced APIs. It comes with a lot of advanced features like macros and shapelets. Those are great tools for doing code generation and like reducing boilerplate. So it makes it easier to write complex pipelines with very little code. So we built Scio. It is the Scala API on Apache Beam and Google Cloud Dataflow. And it's open source on GitHub, so you can check it out, github.com/Spotify/Scio. A classic WordCon example, you've seen this for pretty much probably for every big data processing framework out there. And this one is actually very close to what the Sparks and Scouting ones look like. So basically creating a context to describe an abstraction of a data pipeline. You read a text file, in this case some Shakespeare text, and you flat map it by splitting the strings by empty spaces, filter out the empty words, and you count by value, and then you get your word count, save it to a text. You close the context to run the job. And slightly more complex one, PageRank. And even in this case, it's a dozen lines of code, and you can do 10 iterations of PageRank by emitting ranks and then like divided amongst outflowing links. So it's pretty straightforward. All right, so why do users use like Scio? Why is it a great tool for us? It actually offers a couple of things that's missing in the Java API. One of the most popular one, the users that's heavily used within Spotify, is type-safe BigQuery. So BigQuery, it is a SQL analytic tool on Google Cloud. The BigQuery native API gives you access to data rows in the form of JSON, and it's untyped, so it could be like a lot of trial and error to get your query right and then get your code right. In our case, we use Scala macro to generate type-safe case classes at compile time. So in this case, we have a query that selects ID and name from a certain table with a class user. We don't have to handcraft code to populate the fields in this user class, and it's generated by the compiler for us. And this gives us a pretty high confidence that if our code compiles, it's actually checked against the actual data schema in the services, and we know we have a pretty high confidence the code will run correctly, and then we're unlikely to run into any cast error or null point exceptions, common errors that you run in big data pipelines. This is actually one of the most popular part of Scio, and one of the early adoption case. And Adam, the engineer on Discover Weekly and Release Radar, rewrote the original code and then actually reduced lines of code and also speed up things because we can use the best of both worlds. We are leveraging BigQuery for its columnar storage and its execution engine for doing the boring stuff. The boring stuff being like selecting columns and filtering rows. And then we plug the data into Scala for the interesting stuff like doing machine learning, vectors, numerical computation, and all of this in the same code base, oftentimes in the same file, and makes it much easier to tweak algorithm on the go. We have a couple other things that we built on top of the ecosystem. We have an interactive repo, so you can explore data like more interactively. We baked some enhancement into the visualization. So from the graph, I can actually see the file name and the line of code from the original source file. So it makes it much easier to debug user code. A lot of the times when users ask questions, they just send me a job link, and I can easily identify there's something structurally wrong or like unsound in the graph, and that's a great tool to have. And we also added a lot of optimization under the hood. Like there are multiple ways of doing joins depending on the size and shape of your data. We added all of these, like battery included. That's one of the philosophy. Basically, anything that's error prone, anything that user has to handcraft, we try to bake it into the system to make it easy. And we also build a lot of libraries and ecosystem on top of Scio. One of the more interesting cases is called Big Diffie. So it's kind of like diffing, but instead of diffing two files, we can diff two records, right? So if we know the two records with same schema, and then we know the types of the fields, like integer, float. The difference is just the numerical subtraction, but strings, it could be like edit distance. If it's a vector, it could be a cosine similarity. And given that, now let's say instead of 2 records, we have 2 data set of records and a key function. And then we can compute a diff on a key per key basis. And once I have that, I have a collection of differences, right? And then collection of differences on different fields. Now I can compute statistics, like which field has the most difference, what's the standard deviation, what's the mean and maximum and minimum value of such field, and use that and any simple statistical analysis technique. I can build interesting use cases like checking whether machine learning algorithm has regression. And the most common use case for this is actually checking whether I port a pipeline that's compatible with the existing one. For example, we ported a lot of Python pipelines with no test to Scio, and then by just diffing the results of the different versions of the Scio versus Python pipelines, on the same input data, we can easily check if the pipeline port is correct. So it gives us a lot of interesting information, like how many fields, how many pairs are same, different, is it missing the left-hand side, right-hand side? And on a field level, what's the statistics of the field differences? And the use case, as I've said, it's proven to be pretty useful in our migration to Google Cloud. Another interesting use case is a library called Featurean, and it's a tool built for feature transformation, specifically for machine learning. So if you've done any machine learning, one of the most tedious tasks is actually feature transformation, like taking a lot of column inputs, say normalizing numerical values or transforming categorical values into vectors, common task like that. And oftentimes in a machine learning workflow, we have to tweak these features over and over until it fits or like produces useful machine learning models. And in this case, we built it like feature as a DSL on top of Scio. So instead of writing the actual handcraft pipeline, manipulating fields and doing calculation by hand, the user can describe what type of transformation I want to apply on each columns, and then have the code auto-generated and runs on Scio. And it actually supports a couple of other backends as well. The operation is actually super simple. Look at this case. We have a case class of user account with a couple of fields, integer, double, and a string, which is a categorical data type. And instead of writing like data pipeline called map reduce map, we write a spec, which describes how I want to transform the data. What do I want to do to each one of the field, age, income. I want to apply standard scaling or quantile discretizer or one-hot encoder. And this code gets translated to a map reduce job, or in this case, a Scio job with a single reduce step. And at the end of the operation, I can extract the featureized or like transformed features as numerical vectors, which is suitable to be fed into a machine learning algorithm like TensorFlow or Scikit-learn. And I also get other like metadata from the data sets, which I can plug into backends or some kind of meta store. And that's it. That's the Scio part. All right, thank you.